Okay, this is going to be Unit 7 lecture for ELTN 132, and we're going to talk about logic families a little bit. There is a lot of information, and I'm just going to really kind of focus on the parts that I think are significant or important for the basics of what we're trying to cover in class. So we're going to look at are these different logic families, and then the voltages and currents associated with them, particularly the input and output voltages. The two types of families can basically be divided into two general categories, what is called TTL and what is called CMOS. TTL stands for transistor logic, and these are used using what are called bipolar transistors. And then CMOS technology, which stands for complementary metal oxide semiconductor. I'm not going to write those out, but you can find those in the book. The TTL family is much older. I believe probably, maybe mid-70s, late 70s. And the CMOS came in after that. And just in general terms, the TTL devices were using bipolar transistors. So, for example, NPN or PNP transistors, which had some advantages, but also some disadvantages. The CMOS devices used a completely different technology where they're using basically like field effect transistors on the outputs. And a couple of big differences between these. So I'm going to draw these kind of like what they typically show as a field effect transistor. And we're not going to get into a whole lot of detail about the differences between these, but just a few things that are important. First of all, when you think of TTL, this is the older family, it uses more power. And the CMOS devices are very low power devices. And that became significant, obviously, as you started getting larger systems that were trying to be designed to be in portable systems. Low power became much more significant. So when we think of an inverter, symbol that we typically use looks like that. We've kind of up to this point said that a logic high, a 1, equals 5 volts, and a logic low equals 0 volts. And that's not entirely true, and we're going to see that there are some differences between these. But the question is, what is inside this symbol? Obviously, if you opened up, or maybe not obviously, but if we opened up an integrated circuit, you would not see this little triangle with a bubble on the end. That is a symbolic representation of the logic function that it performs. We're taking the input and inverting it from a high to a low or a low to a high. Also, we'll talk a little bit about, a very little bit about propagation delays. That change does not happen instantaneously due to capacitance and other factors in the circuit. So let's take a look at what's inside this inverter. So this is on page 155 in the book. And what we have on the left here in figure A, trying to find something to point with here, is a TTL, transistor logic inverter. And on the right we have a CMOS inverter. Now right away you notice some pretty substantial differences. Which looks more complicated? Well, if we simply counted the components between these two, on the TTL device, we have 1, 2, 3, 4 resistors, 1, 2, 3, 4 transistors, and 2 diodes. On the CMOS device, we have 2 output devices, CMOS transistors, they're called MOSFETs, and 2 diodes, which are used to basically clamp the voltage from overvoltage coming in on the input. So you could see or imagine pretty quickly that this device would be a lot easier to manufacture than this device with all these components. And so this is where the technology changed quite a bit. Now, the other thing that's significant here is that, and in chapter, I believe it's chapter 8, they actually go through how this input will turn on the output voltages here, a low or a high, on the output device. But if you take a look at it, this is referred to as what they call a totem pole output. That's because all these components are vertically arranged. And neither of these transistors are on at the same time. Either Q4 is on and allows current to flow out of the device, or Q3 is on, which allows current to sink to ground. So if Q4 is on, we have current flowing from the positive rail through this resistor, through the transistor, through the diode to the output. We'd have current flowing out. If Q3 was on and Q4 was off, basically nothing is connected above that point and all of the current goes to ground. But what's important here is that their voltage drops across this resistor, across the transistor, and the diode for a high output voltage. And what that basically does is it takes away from the 5-volt output, it reduces it to something on the order of between 3 and 4 volts. Same for the output here. A transistor, the VCE, the voltage when a transistor is turned on between the collector and the emitter, might be anywhere between 0.1 and 0.3 volts. So that means it doesn't really go to 0 volts, and we'll see that in a moment. However, the CMOS device, when these devices are on, it's without getting into a lot of the technology side of things, basically the output of this looks like a resistor. And if the transistor is turned on, if the MOSFET is turned on, the resistance is very, 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 very low, to the point where almost your full supply voltage, let's say it's 5 volts, is outputted. And if this MOSFET is turned on, it's almost connected to ground with what looks like a short circuit, very low resistance. The output impedance is very, very high. And so when one is on and the other is off, what you end up with is a voltage that's much closer to the supply voltage than the TTL device. And that has some advantages. Let's take a look at those real quick. So if we take a look at a data sheet for a typical TTL device, whether it's a inverter or an AND gate or whatever, they have different voltage ratings for these output high and output low voltages based on the transistor circuits that we were looking at just a second ago. So for the low voltage, the minimum typical level would be 0.2 volts. The maximum low or 0 value would be 0.4 volts. For a high, the minimum has to be 2.4 volts, and a typical value is 3.4 volts. So that might be a little surprising. We're thinking, well, it should be at 0 volts or it should be 5 volts. But in reality, because of those other components, there's some kind of a difference between those two. So those are the output voltages. Now let's take a look at the input voltage requirements. Now for the TTL input voltages, it looks a little bit different here. What we have are what are called VOIN max, that's the low input maximum, and the VIH minimum. In other words, it can be anywhere from 2 to 5 volts, that's fine. And that would read as a logic 1. And anything below, in this range, below 0.8 volts, 0 volts, would be read as a logic 0. But how about this area in between? Well, that's a problem. If you had a voltage, for example, a 1 volt input on our inverter, there's no guarantee what the state will be. It could be low or high. And so we kind of consider that area kind of like, I guess what you call no man's land. We don't want to, that's an unallowed state. So that if we have devices hooked together, we have to make sure that the voltage for a low is no greater than 0.8 volts, and that a high has to be at least 2 volts. And this is going to be important when we talk about what are called noise margins in a second here. So the output voltages and input voltages are not the same. They're not exactly 5 volts. We'll see CMOS in a second here, but what I want to show you next are where we compare the inputs and output voltages and why that's important. Okay, and this is on page 493 in the book. I know I'm jumping around a little bit, but for some reason they really kind of broke these parts up in kind of what I think is not the most logical arrangement. So what we're looking at here on the left are the output voltage ranges for TTL, and the input ranges. Now, they don't have exact values here because this is more of kind of a generic picture. But the point is this, is that our logic output has to be less than the expected logic low input, and the logic output high has to be higher than the minimum high input. And what we have between these two are what are called the noise margins. That's, for example, if we had some noise, if we had some signal that was actually like a little pulse riding up above here, it might cause a problem. And for TTL, the noise margin is pretty small. And that is one of the problems or disadvantages with TTL, that if there's noise in the system, it's more susceptible to the noise. So already you can start to see some of the disadvantages with TTL. It's higher power, and the noise margin isn't that great. Now, it doesn't mean it still can't be used, but you have to be a little bit more careful how you use it. Okay, so here's, I'm going to include this as a web reference also. This is also kind of a good way to visualize this, probably a little bit better than my sketch. What's important is that we're looking at inputs on the left and outputs on the right based on this gate with a supply voltage of 5 volts. So this is basically what I was driving at before. The high voltage, anywhere from 2 to 5 volts, is an acceptable input voltage level. Now there's a minimum level, but the maximum is still 5 volts. You can go above that. For the output, however, the output is 2.7 volts, maximum to 5, and the low in this case is 0 to probably around the order of 0.2 volts, something like that. So this picture shows a little bit better kind of the difference, what they call the noise margin between these. In other words, what our input is compared to our output, how much of a range or an error there that we could have between the two. Now let's take a look at CMOS. CMOS is very different. First of all, sorry, I got some K-map stuff left over there. So first of all, we'll notice that the input signal levels for CMOS are not terribly different. The low is a little bit higher, but the high is similar. But look at the output levels. This is what's amazing. The output level is almost 5 volts, 4.95 volts. And the low level is from 0 to 0.05 volts. So you have a much greater difference between these. And what's the other thing that's interesting, and so that changes our noise immunity considerably. Now the other thing that's important here that I failed to mention in the beginning is that we typically are working with 5 volts for logic levels. They can actually go down to 3.3 volts or lower. But CMOS, one of the advantages is that you can actually supply a higher voltage. So let's take a look at this, what we can do. If we use 10 volts instead for our supply voltage, now you'll notice these much bigger gaps between the low and the high. And that also the output levels, again, are almost 0 volts and almost the supply voltage 10 volts. So that basically changes the noise immunity, how susceptible a device is to noise. And I'm going to leave it at that for now because we could talk about that for a couple hours probably. And if you're interested in more information on that, you could take a look at those chapters I listed. Now, one of the things that's important about this is not only the noise immunity, but the danger you can get into if you accidentally interface the wrong families of devices. So for example, if we had a TTL device as an output, and its output minimum was like 2.5 volts, but the input to a CMOS device, it was expecting something more on the order of 4 volts as an input level, the output from the TTL device would not be high enough. And so it would never supply a voltage high enough to turn on the inverter for that CMOS device. So one way we can work around that is to put a pull-up resistor here, but it's not a very elegant solution. So the best general rule of thumb is if you're working with TTL devices, and these are like the 7400 devices, XX, that you stick with staying with those families. CMOS, same. If you're working with CMOS devices, it's a little safer to stick with those. Now, what's interesting, and I haven't really told you this, is that the devices you use are labeled, for example, 7408. But what that really, the device, if you peeled up that little label I stuck under there, it's actually a 74HC08. And what that stands for is high-speed CMOS. So even though it's the same logic family as the TTL devices, and it has the same footprint, it has the same schematic symbols, it's actually a CMOS device. And all of the devices that you have are CMOS. I chose those intentionally so you wouldn't run into this problem where the voltage levels would not work together. Okay, I know I'm just summarizing a lot of just very basic points, but I want to touch on this because it's more of a gotcha than anything else. I remember working on circuits where I accidentally mixed different families of devices together and I could not troubleshoot or figure out what was going on. And that's a common problem with that. Now, the other thing that we look at, besides the voltage levels, are current levels. But before I do that, I want to just define some of these terms that you'll see that'll probably pop up in the book. So for the input to a device, if we're looking at the input of a gate, for example, an inverter, we talk about the VIH. That's the input high voltage. And that's typically a minimum voltage to trigger the device. So for example, if that was 3 volts, that'd be the minimum voltage up to 5 volts that would produce a high or a 1 as an input, or be read as an input. The other term that's used is VIL, and that's usually a maximum also. So VIH minimum, it's got to be at least 3 volts to trigger it. VIL, there's a maximum value here, which might be, for example, 0.8 volts, something like that. And anywhere within that range of 0 to 0.8 volts would be valid as a 0 input. The output, VOH, would be considered a minimum, and VOL would be considered a maximum. So again, if you read through the chapters in the book, it explains this a little bit more, but I want to explain what those terms. The V is the voltage, O or I are the subscripts for input and output, and then H and L are high and low. High being a logic 1, low being a logic 0. So I just want to try to avoid any confusion with the terminology. Okay, so now we're looking at our currents. And currents are important because it really restricts how many devices we can connect to the output of a single gate. You can't just connect an infinite number of outputs because there's a certain amount of current limitation. So in this case, Q4, when it's turned on, will do what's called sink current. Current will flow through that output to ground. When Q3 is turned on, it sources a certain amount of current to the output. It puts out a certain amount of current. Now, interestingly, typically these TTL devices can sink a lot more current than they can source. And that's a lot of the times why you'll see we'll be talking about negative logic and inverted inputs and outputs. They're much more common, and that's because they typically can connect to more devices. So if you connect, for example, what this is showing on the right is the output of a TTL device, and then this is an input where we have multiple devices connected. And I'll draw kind of a logic diagram for this in a moment. And same thing here. We have an output of a device. It could be an inverter or an AND gate. And then these are inputs to other gates that it's connected to. So pretty quickly you can imagine if we have too many gates connected that need too much current, more current than this transistor can provide, what's going to start happening is our VOL voltage will start to drop. And it'll get to the point where it actually will not function anymore. Actually, in this case, the OL voltage would probably increase. The transistor simply cannot provide enough current to drive all of these outputs or all of the inputs from these other devices. The term they use for this is what is called fan out. And so, for example, if this device could only drive 2 outputs, it would be called a fan out of 2. If it could drive 10 devices, it would have a fan out of 10. So let me show you what this looks like from a logic gate perspective. So here's a real simple logic circuit. We have an inverter driving an input to an AND gate and the input to an OR gate. So what would the fan out be? In this case, because there are 2 devices connected, it has a fan out of 2. It can drive 2 devices. However, most of these TTL devices have a fan out anywhere of 10 to 15 or 20. And if you try to connect too many outputs, if we keep connecting these to other gates here, if we drive other gates with these, eventually we'll get to a problem where the device cannot sink enough current or source enough current to drive all of those devices. So we can't just connect this to an infinite number of gates. Now, what if we wanted to drive more gates? Well, we could use a transistor to amplify that current, or we could tie that output to a couple of other devices here, and now we would increase our fan out to other, since this only would have a fan out of 2, we're only connected to 2 inputs, but if each of these could go to 5 more outputs, we could drive a lot more devices. Now that ends up being a little bit of a problem. We talk a little bit later about propagation delays, because the time that that output would go to a low would not be the same time that these other outputs would change. Actually, how I should probably draw this is with 2 inverters, like that. And sometimes you'll see that in these devices. Sorry, this is getting a little messy here. So that the logic state on this output is not changing. In other words, this is low, that would translate to a low on this output. So that's one way you can avoid the fan out issue, although it's not that common. Usually we're only connecting an output of a device to maybe 1 or 2 or 3 different gates. So let's take a look at fan out for CMOS devices. This is on page 527 in the book. Now, CMOS devices take a tiny, tiny amount of current to activate. In fact, the input impedance, as they show in the book here, the input resistance is something like 10 to the 12th ohms. So it's drawing almost no current. However, so in theory, if all we were concerned about was current, you could drive probably 1,000,000 gates with that output because the input current is so small, and the output current is probably in the milliamps range, probably on the order of 10 or 20 milliamps. However, what you have to be a little careful with is that each of these devices, because the input impedance is so small, it almost looks like a capacitor on the input with a capacitance of 5 picofarads. And if we keep connecting more and more of these devices together, you're increasing the overall capacitance of the input. Now, going back to 130 or some other classes, and we discussed this in 131, capacitance basically affects the rise time and fall time of signals. It adds a delay as that capacitor charges and discharges. And so the effect that this has on the CMOS circuits is it can limit the frequency response of how fast these devices turn on and off. Now, interestingly, you can go all the way up to 1 megahertz and have 50 devices connected. But if you're trying to operate something at 30 or 40 or 100 megahertz, then that would become a consideration. The time it would take for that gate to turn on or off would actually slow down. So it's not a current problem here with the fan out, but it's a time problem or a frequency response problem. Okay, so those are some of the things I wanted to talk about with voltages and currents, with the TTL and CMOS devices. I'm kind of highlighting these topics. I hope that you will be able to read through the book and go through those chapter sections and get a better understanding of the importance of current and voltage and why we have to be careful about the logic voltages that we work with when we're interfacing these devices.